So we're here today to talk about Project Leyden's AOT, shifting startup into high gear. I'm Dan Heidinga. I'm a runtime architect with the Java platform group at Oracle. All right, so let's jump in. When we talk about application performance, we often look at sort of that peak performance, the long tail or the stabilized performance when we've hit the max that we're going to get from the system. And we're working on driving the amount of time that each operation takes to get it as little as possible. And this is where we focus, right? Typically long-running applications, we're getting that peak performance, and that's the piece people worry about. But our industry's changed in a lot of ways. We've shifted to different ways of doing deployment, so things like microservices where we're scaling up and down different instances at different times, where we're adopting things like continuous deployment, so we're deploying code more frequently than we have before. And this startup and warm-up, this early part of our graph, starts to dominate and take up more time in our application's lifecycle than it has before. Well, that's our startup and our warm-up, so it's a good thing that Project Leyden is looking at that. So what's Leyden doing? Well, Leyden is looking at, as I said, the startup and warm-up of Java applications. So I'll give you sort of some rough definitions, so we're sort of all talking about the same thing. These aren't perfect definitions. Different ones are perfectly fine as well, but it just gives us something to sort of think about. So let's define startup as the time it takes to do the first useful piece of work in your application. If you have a Hello World application, that's the time it takes to print Hello World. If you have some kind of app server, that's the time it takes to respond to your first request. And warm-up is, sort of from that startup time all the way through until you hit peak performance. Now, peak performance itself is not always a clearly defined or easy to say that's peak. So these definitions and these phases are a little bit fuzzy as well. And this includes the time done by your application, maybe you're parsing configuration files, as well as work done on behalf of your application, loading and compiling classes. And startup and warm-up are an issue for Java because Java is highly dynamic. What do I mean Java is highly dynamic, right? We typically think of Java as being static. Now the problem is static and dynamic are terms that we abuse in a lot of ways. And one of the most common ways to abuse them is to say that static means at compile time and dynamic means at runtime. So I'd ask you, is Java statically typed or dynamically typed? But the answer's on the slide, so I won't bother for a show of hands. Java has a static type system. Java-C enforces this at compile time. It also has a dynamic type system that's enforced by the VM at runtime. And the two overlap. It'd be pretty strange if they didn't. But they do have different rules and significant differences. The static type system has a bunch of things in it that aren't in the runtime type system. We have generics, we have checked exceptions, we have definite assignment analysis, we have overload resolution. And the runtime type system has things that the compile time system doesn't. It has things like array store checks. There's no way Java-C is going to be able to detect that for you. Okay, so Java's both statically and dynamically typed, which means our definitions of static and dynamic aren't great. So when we have to backpedal on those kinds of assumptions, a good thing to do is go look, what does the dictionary say? So if we look at the dictionary definitions for static, we see that there are a lot of things like without motion, at rest, little change. So we're talking about, when we talk about things that are static, we talk about things that don't change. And when we look at the definitions for dynamic, we see continuous and productive change. We see energetic, we see motion words. So dynamic is about things that are changing. Okay, so if we're talking about what's changing and not changing, then we need to look at what are those things that are changing. So in the context of languages, we often only think about static and dynamic type checking, but there are a lot of other things that are going on. Java has dynamic typing. Java has dynamic class loading and verification, class redefinition, dynamic compilation, our beloved JITs, dynamic recompilation after we de-optimize for some reason. We have dynamic linkage, right? When Java talks about some other field or some other class, it's all done symbolically. We don't hard code addresses. It makes it so we don't have to recompile the world when you drop a new jar onto your class path. We have dynamic dispatch. We have dynamic introspection, like instance of and reflection. So Java's pretty dynamic. Okay, so if Java's dynamic, then we have to look at, not just what's changing, but we have to look at over what period of time it's changing. So if we look at things in Java, we see that there are a lot of interesting phases beyond just compile time and runtime. We've already talked about 3 earlier. We talked about startup, warm-up, and peak performance. But there are other phases and other pieces that we could talk about where they change and over what period of time. So I have a nice line of code here that says static final int seed equals cesium sample.get random number. Is this static or dynamic? Well, it says static, so that's a good hint. But it's an initializer that runs at runtime, so that seems dynamic. But the value is held final, so it doesn't change after we set it, and it stays set to that value for the life of the application, or at least until that class is unloaded. So that sounds, static again. So we don't really have this nice compile time, runtime piece. We have a bunch of things that are born dynamic that appear to be static later. And Java is really good at taking these things that are dynamic in some way and making them appear static, and then being able to optimize through that. Okay, so what we see here is that Java is not a choose one, lose one, but a pick both. And pick both in ways that we can balance and give you good performance and good optimization and a good user experience by giving you both. Optimizing entities that were born dynamic into ways that make them look static is a core JVM competency, right? We take static fields and then we use them throughout the code without having to go reload them each time. We can make decisions based on their values. We use class loading that's dynamic, but once loaded, we keep it and treat it statically. We're also really good at hiding the evidence when we've speculated that some hierarchy isn't going to change, and then it does. If we have an interface that only has one implementer, we want to be able to inline that implementation everywhere it's used. Oh no, you've loaded another implementation of that interface. That's fine. We'll de-optimize, we'll re-speculate, and we'll optimize again for you. So Java's really good at being both dynamic and static, and good at hiding the costs of that dynamic nature. What does this mean for startup? Well, let's talk a little bit about what happens at startup. There are a lot of things your application is doing at startup. Your application is reading configuration files, it's scanning for annotations, it's opening sockets, it's creating loggers, and probably more loggers, and probably more loggers. And the JVM is doing a bunch of things for you as well. It's loading the classes that you've referenced, it's linking those classes together, and then it's initializing them. When you mention a class name, we have to go off, read the class file from disk, load it in, verify it, turn it into internal metadata that we can use during the execution of the application. We run the static initializers. The interpreter is along there chugging away, starting to get your program going so we can find more classes to load and more things to do. We're linking call sites, so invoke dynamics for all your Lambda expressions. We're resolving all the dynamic information, all the symbolic information that gives us the references between classes and turning them into addresses and offsets and things the VM can use for its execution. And the whole time, we're collecting profiles. Okay, and then what happens at warm-up? Well, warm-up is your application has started responding to requests, so it's probably building its own caches, saving away state for different things so it can optimize later requests. And the JVM is coming along and compiling your methods. We're figuring out which methods are hot enough and spending the right amount of our compile budget on those things. Okay, so this seems like a lot of work to do every time. Why do we do it this way, right? Every time you run your application, you are going to load object, you are going to load class, you are going to load string, you're going to load thread and module, and all the classes that they depend on. So why do we do it this way? Why do we make these things have to happen every time? And the reason is that this is the way the ecosystem wants things. It makes the language more expressive for you. It makes it so that you can use things like on-the-fly class loading. You don't have to close your world. It makes it so you can use reflection, so you can use all of these more expressive things that are built on top and built on this dynamic nature of Java. And it means that we can give you great peak performance. We are really good at reading the machine you're on and using the best instruction set for the machine that you're actually on when we compile code. At profiling the data so that we're not guessing at what the path you're taking is, but taking the actual path that your application is following. We can use the characteristics of the machine you're on, of the application, of what you're doing to be able to give you good optimization. But all of this dynamic behavior comes at a cost. And that cost is your startup and your warm-up. It means that we are a little bit slower there than we'd like to be. But this is a great trade-off for most applications. Anything that's, a longer running application benefits a lot from the peak performance that we can give. Now, if you're a command line argument or a command line program that's only going to do a very little bit of processing, this startup and warm-up trade-off might not be the best for you. But it really does work out well for a lot of use cases. And just to emphasize that, there was a post by Scott McNeely on LinkedIn in which he talks about being able to do plugin architectures. And the fact that we can take a set of jar files that are different plugins, drop them into place, load them up and use them without having to recompile the world, without expensive RPC or other kinds of difficulties, is a real benefit of Java. It makes all of the applications and the code and things that we depend on easy to work with day to day. Now, at this point, we've said Java's highly dynamic, and we like it that way. We've said Java is good at speculative optimization. Now, what if we could take that speculative optimization we've been doing and extend it in different ways? So Java is really good at taking things that were born dynamic and making them look static. And it does this by observing what the program does, observing its behavior, and then turning that into speculative optimizations that assume that prior behavior is going to predict future behavior. And we have dynamic recovery paths when that behavior changes to hide that we've done something. Okay, so speculative optimization, that's awesome. And we've talked about the static and dynamic spectrum, but there's a second spectrum here, and that's when things happen. Just in time says I'm going to do things as I need them at the last sort of possible instant to be useful and to compile things sort of when the benefit of compiling it outweighs the costs of not compiling it. And ahead of time says I'm going to do something early. Now that doesn't necessarily mean we're doing it all the way before runtime. It might just mean earlier than we had to do it. Java has, interestingly, always supported early resolution. It's been legal in the JVM specification to resolve entities much earlier than when you actually talk about them in the application. You just have to preserve the error behavior to throw the errors at the right places. Okay, so if speculative optimization is so good, what if we could take that and extend that beyond one application or beyond one run of the application to be able to say, this previous run is going to be a lot like my next run. What do we get? Well, we get training runs. A training run says, let's exercise that startup and warm-up code that we're worried about optimizing. Let's observe that execution. So we can discover ahead of time what we would only have otherwise discovered in the early phases of execution. Okay, so what is a training run? Like what would we use for that? Well, the best training run is to run your application. If you're doing canary deployments already, maybe your canary is a great thing to use as our training run. We can observe how your canary behaves and use that to speculatively optimize your subsequent deployments. But we can also use some integration test or something else that runs in your CI pipeline. Some small driver program that has the same kind of behavior as your actual application, so that we're driving those same code paths and getting the right the right profiles and the right observations to drive our later work. Training runs are effective for the same reason dynamic compilation is. They allow us to observe what's actually happening. And we found that they are quite unreasonably effective. We expected to need to do more static analysis when we started this project and have found that training runs get us a long ways. So if we're not used to thinking about training runs, what's interesting is that they're already in use. The JDK often ships with a default CDS archive, which was created based on a training run to figure out which classes we commonly use. So that means that we have some cached metadata for a lot of the classes that we use in every run of the JDK. And app CDS is the same idea, extended to applications, to be able to say, oh, those classes that you use are going to be the same. And so we can benefit from having seen that before to optimize later runs. Now, with CDS, we can only make very minor speculation. We can say the class that we saw is likely to be seen again, so it's worth saving the VM's internal representation of that class somewhere where we can reload it and reuse it. And that is definitely a performance improvement. But we can't speculate across those classes. We can't speculate about the relationships between the different classes. And part of that is the way CDS is designed. So if we look at what CDS does today and treat that as sort of today's AOT, or pre-JDK 24 AOT, what we see is that as you execute your program, you hit the first time where you go to define a class. And that goes off and asks the VM, hey, can you define a class named foo? And it goes off and checks the CDS archive and says, oh yes, I do have a pre-parsed form of this. Let me give that back to you. And we load that and use it. And then you continue along, and the next time you go to load a class, the same thing happens. We go off to CDS, we adopt the asset from CDS, and now we've got something that saved us a little bit of work in there. Now this is useful, but it doesn't get us very far. It gets us to having a more optimized path to get that data into our VM, but it doesn't get us linkage between the different classes. Because there's a lot of things where we may be able to use one class from a CDS archive, but not another. Maybe you changed one jar between creating the CDS archive and so the bytes don't match anymore and we're not able to use that class. Maybe you changed your command line options or did something else that invalidated the speculation we're doing here. Now, what we need though is some way to get more out of this. And to do that, we had to look at how does the JVM execute? And in particular, we had to look at what happens before main runs. We tend to think of our program starting when our main method starts executing. But there's actually a lot of things that happen before that. It's kind of a conceptual phase that we call pre-main. And in that phase, things like the VM is starting. It's allocating memory for the heap. It's starting threads for the JIT compiler. And it's loading all of the classes that we need every time, like class and string and object, thread, module, name, class loader. There's a whole bunch of these classes that every time we go to run, we need. And they get loaded before we start loading your code. So if CDS lets us shift some of that class metadata and metadata creation earlier, and we have this phase where the VM is kind of driving execution, what if we kind of tie those things together? What do we get? Well, we get an AOT cache. So rather than using CDS to, on a request-by-request basis, load each of these classes, we take the set of classes that we observed in our training run and load them in bulk. Because we're adopting them as a large set, we can now say, I know that these two classes that have references between them are loaded at the same time. So I don't have to wait until later to go and do that linkage between them. I can do that linkage now. I can do that ahead of time. And this means, though, that I can't only load one of these classes. I can't say, oh, I don't need that particular one, so I won't load it. So we have a small constraint here that says that if I'm going to use my AOT cache, I have to load all the classes at once. But this gives us a foundation to build on. It gives us something that is a stable address that we can start to associate with other data. By having a stable address, we have something that we can talk about between runs to tie other data to that. Otherwise, just having a class name isn't enough to really identify a class in a running VM. You need both a class and the class loader. That pair together is what really identifies a class. So by having all of this pre-linked and preloaded, we're able to have that true identity. So we talked about what happens at startup. And what we've seen is with our AOT cache, we can address the things that are marked here in yellow. The class loading linking, and the call site linkage. Okay, so let's talk a little more about this. So as I said, inside that AOT cache, we can have two classes that are set to point to each other using their addresses, not their symbolic information. And that's a pretty cool thing, because it means rather than having to say, oh, every time you use this name, I have to go find it, it means I can have that linked to the other address already, and I can start in a resolved state. It means that I can have my class know its superclass and all the interfaces it implements. It means I can have the field layouts figured out ahead of time. I can have the vtables figured out ahead of time. And I can start to resolve constant pool entries. The only constraint is that these things have to all be loaded together. So when I mentioned the constant pool entries being pre-resolved, let's take a little bit of a deeper dive into what that means. So I have a very small program here. It's got a list of words, and it creates a stream over that list of words. It uses a lambda to filter them, and then it joins them back together and says hello world. And if we look at the class file for this, what we see is we have really 39-byte codes here and a bunch of symbolic references. So if I look just at that first line of code, and I don't expect you to read all that, it's a little bit of an eye chart. That first line of code says words.stream. So at runtime, that first byte code, that get static of number 1, has to know where do I find words. And so we have this symbolic information that tells us that's the name, that's the class you have to go look in, that's the type of the field, go and make sure you find the right one. And we see in our second thing is an invoke interface. Well, we have the name of the method, but not the actual address, and so or the itable index. So you have to go and find that. We have an invoke dynamic for our lambda expression. And if you know how invoke dynamics work, what ends up happening at the first, if you know how lambdas are translated, what happens when you run that invoke dynamic is we generate a class. That class gets generated, and then we wrap it with the right objects to be able to use it. So what we want to do is shift all of that work out of our execution, so we're not doing that each time. And that's what we're able to do with our AOT cache. Instead of keeping the symbolic data, we now keep the field offsets, the itable offsets, the call site object, and a bunch of this data that's the language that the VM uses. Okay, so that's really cool. We can shift this resolution. Where does this resolution shifting happen? Well, with JDK 24, we have what's called a 3-phase workload. The first phase is our observation phase. It's where we do our training run. We run this with -XX AOT mode equals record, and we give it an AOT configuration. And so we make a bunch of observations, we record them into this configuration file. Next, we do an assembly phase. And the interesting thing with the assembly phase is it does not run your application. It runs the JVM just enough to be able to load these classes, to resolve things, to put things into the right state, to build our AOT cache. And then you do your deployment run using the AOT cache. If you're more of a visual person, what it looks like is a little bit more like this. Training run, and that passes the configuration to our assembly phase. Our assembly phase executes and creates an AOT cache, and that cache can be used for numerous deployments. And the reason we do it this way is that we have a clean separation between the training run and the assembly phase. It ensures that we don't accidentally carry state across from that training phase into the assembly phase. We don't want to change the meaning of your behavior. We don't want to change the meaning of your program by accidentally carrying across behavior that's not reproducible. And if you're interested in more details, you can take a look at the JEP 483, ahead of time class loading and linking, and that's what we've delivered in JDK 24. So what does that get us, right? I mean, class loading and linking, that can't be that much, right? Well, if you were at the keynote, you already saw these graphs, but what they show here is that they show a number of frameworks and sort of the getting started applications for those frameworks for Helidon, Micronaut, Quarkus, and Spring Boot. And we see not a comparison between the frameworks, but a comparison of JDK 24 out of the box versus the JDK 24 AOT cache after a training run. And what we see in most cases is a 2.5 to almost 3 time startup improvement just by caching the classes in the resolution state. The next thing we see on this is this green bar, which is the Leyden early access build, where we've got some additional optimizations in place. And we see in some of these cases, not a whole lot of extra improvement from the Leyden EA builds, and that's because these are getting started type applications, so they don't do enough execution for this to matter as much. If we look at the Spring Boot Pet Clinic, though, we see that by adding the additional optimizations in, we get more of an improvement, and that's because Pet Clinic is a bit of a slightly larger application. Okay, so if the gray bar is what we've delivered so far, what's in that green bar? Well, the first piece is profile gathering. This was one of the other things that happened at startup that we hadn't addressed yet. So let's look at this a little more. Okay. So why does the JVM profile? Well, we talked about being able to do speculative optimization requires observing the behavior of the application so we have something to speculate on, and that's what profiling is. We want to record observations about the behavior so we can drive what the JIT does. And it's primarily collected for methods that are hot enough. We don't want to collect profiling data all the time because there's a cost to collecting it. So we want to make sure we're collecting it for the right methods. And that'll drive recompilation at higher tiers. And the kinds of data we collect are things like method invocation counters to find out which methods are hottest, branch frequencies to figure out how your data flows through the system, the classes encountered to make sure that we're compiling for the right things and able to inline well. So training runs allow the JVM to speculate that previously collected profiles are going to continue to match. Just like we speculated that the classes that you loaded before are going to continue to be loaded in later runs, we're speculating that the profiles that we collected in our training runs will continue to match. Now, if they don't, that's fine. We'll just decompile and reprofile, right? This is our speculation with fallback. So JEP 483, the ahead of time class loading and linking work that we talked about, provides us sort of a stable anchor to tie these profiles to. Because now we know that this class is this particular class and the relationships between it and the other classes, we now have something stable to tie that profile to. So when one profile talks about another class, we know exactly which class it's talking about. We don't have to speculate as much, we know. And we're not limited. We're not limited to the AOT profiles. We're able to continue to profile at runtime so we can have another choose both situation. And this is great if that allows us to get out of these profiling code earlier. So maybe we have enough profiles that we can jump straight into higher level compiled code. Maybe we don't. Maybe we have enough to be able to do a little bit more profiling and then jump earlier than we would have otherwise. And we can continue to profile if something doesn't match. So we have a JEP draft for this called ahead of time method profiling that's working on trying to make sure that those profiles are available early enough that we can do interesting things with them. Okay, so that covers a lot of what we've talked about in sort of the startup phase. When we get to warm up is what everybody thinks about when we talk about AOT. We start to talk about JIT compilation. or code generation in general. Now, to really understand code generation, we have to remember that all JIT compilation is speculative. Everything that the JVM compiles has an option to fall back and to throw away if it doesn't apply anymore. Maybe the environment changed. A new class was loaded, and the assumptions we made that there were no subclasses are no longer valid. Maybe the profiling data changed, and we found that we thought we were always going down this path, but now we've started going down this path, and we have to de-optimize and recompile. Maybe we just ran out of space in the code cache and decided that it was time to throw something away. Or maybe the debugger attached and we needed to de-optimize to get back to a state where we could show the full view of what's happening in the program to the user. JIT compilation should be thought of as pure optimization, something we can do and throw away at will. All right, but then what about speculative AOT? At this point, we talked about earlier phases. We have the classes that give us stable addresses. We have the profiles that are tied to those classes. So we have good inputs. We have good observations from our training runs. Now we have new options. Maybe we want to take those profiles and do the compilation at startup. This is still ahead of time compared to when we would do it based on method counters. Maybe as we've loaded our pre-main classes, we want to schedule compiles for everything we have profiles for. And that gets that code compiled early in process, and we're ready to go. Or maybe we want to shift that compilation work all the way out of our runtime and into our assembly phase. And then we can take that pre-compiled code from our AOT cache and load it into our running JVM faster. Now, what's interesting about being able to take that code from the cache, if we choose to do that, is that we have to be careful about how we use that code. When the JVM executes, before you can use a class, it has to be initialized. And that means that we have to put some kind of barrier in place to ensure that we don't run code that assumes a class is initialized before it is. So that means we have some class and we want to take AOT code for it. We have options. We can either wait until all of the classes it depends on are already initialized, and then we can load the AOT code and use it. That's earlier than we would have gotten that code just driven in normal JIT execution. But it's still not as early as we want. We're still spending some amount of time executing in the interpreter or lower tiers to be able to get to that state where our dependencies are satisfied. So the other option is to compile JIT code that has these class initialization barriers in it. This code can be loaded immediately and used. The challenge is, though, is that this code is less than optimal. It has extra checks in it that we have to do every time through, even though we've already satisfied the conditions after executing it once. So maybe what we need is not just one kind of code, but two. We need one kind of code that's ready to load immediately that has these class initialization barriers in it, and sort of the fully optimized C2 code that we want to get to eventually. But that means that what we've done here is created effectively two new tiers in our JIT compiler. Instead of having tier 0 being our interpreter and then C1 providing a profiling tier and C2 providing our fully optimized code, now we have this second path of tiers that are always applicable AOT code and sort of fully optimized AOT code. And those tiers are going to interplay with JIT compilation through the rest of the system. Because that's one of the great things about this design, is that we're not limited to the AOT code. If something changes, we need to de-optimize, we need to change how things behave, we can always jump back into the JIT. We can always top up the execution with JIT compilation. As I said, all of this AOT code remains speculative. So if the cached profiles and the cached code are a good representation of how your behavior stays, great, then we get to use that. But it means we don't have to add any new constraints to get here. We don't have to statically analyze your code and decide, oh, these are the only paths that you can take, and if we're not sure, we'll compile something less optimal. No, we get to see this is what you actually did, and we get to compile exactly that without adding new constraints on you. And we get to keep using this speculatively, just like we always have, right? I love this quote, "Success is a habit, but failure is still an option." And when we fail, we just throw it away and recompile. So if some assumption is violated, then we de-optimize, reprofile, and re-optimize, just like we do today. And this copes really well with surprises at runtime. But this isn't surprising. This is what the JIT compiler already does. The key challenge that we face here is figuring out how to merge these new kinds of execution, these new tiers, into our existing system, how to tune the profiles, how to tune the policies that determine which tier we're in and how we transition between them. But I do want to stress again that no code changes are necessary to get here. You don't have to make any changes, you just have to do a training run. And if you're interested in more details on this, there's another JEP draft being worked on called Ahead of Time Code Compilation. And I do want to call out one other piece of code that we're looking at caching is that our colleagues at Red Hat have been working on caching code stubs as well. So these are runtime helpers that do things like exception throws, interpreter to compiler transitions, or compiler to interpreter transitions. It's just another piece of code that we need to get cached so we can use it early. So what have we heard so far? Well, the time-shifting speculative optimization works, right? This approach gives us great gains. It gives us full compatibility with basically no new constraints. We didn't have to change the programming model. We didn't have to change the specification. We didn't have to throw away Java's dynamic nature. We didn't have to tell you you could only use a blessed list of libraries. This just works. And it's largely just taking the things that we had in Hotspot already, rearranging them slightly, and adding some new policies in to manage how we adapt and shift between the different pieces. Now, we understand that training runs are something new, or new to many of us to think about, and that the ergonomics of them aren't great, that three-phase workflow can be a little clunky at times. But we are doing work to optimize that further, to tune that further. And one of the things that would really help us as we do that work is to hear from all of you. So if you're able to, take a JDK 24 build, do a training run, build an AOT cache, and then try using it. Let us know how you found that experience. The more feedback we get on that, the more things that we find out work well or don't work well, the better we're able to adapt what we're doing there. And there's more work to be done. With even just the pieces we've talked about, there's a lot of work to be done to tune the policies, the mechanisms, how we transition between the different pieces. And again, we'd like to hear from you. If you're able to take a Leyden EA build and try that out, we'd love to hear about your experience with that as well. So please do. Pick it up and try it and let us know. And I think I have a little bit of time for questions now. So if anybody has questions, we have some mics here in the front.
Hey, thanks for the talk. The compiled versions with the class init checks, don't they change the initialization order if you then run all the class initializations at once?
The class initialization checks are still done at the points where you would actually access the code. So the spec requires that we do the check on things like a get static. They require that we do it before a before invoking a static method, before allocating a new instance. And so we have them embedded in the code in the right places.
So it means pre-compiled or ahead of time compiled method can have several class init checks, and only when the last of them has been executed, you switch to a method without class init checks?
Yes.
Okay, thanks.
Hey, Cliff Click here. Say something about security. You got a disk file with code in it.
That's a great, a great open-ended topic. I'm not sure why that is different than having a C library or a DLL sitting on your system. So you've got code, you've compiled it. It's no different than having the class files there that you're going to execute. If you have control enough to be able to modify the class files, which are the input to this system, then you had enough control to be able to modify the compiled code as well.
In the C library case, the usual story is the C libraries are set aside in some shared place that presumably require some sort of root and aren't typically have those privileges changed at runtime, whereas in this ahead of time guy, you have to have a CI pipeline which is scribbling new files every time it runs, which just means it's probably not running at its root. Those files are probably accessible much more readily than the C libraries. Is there any thought to detecting or dealing with somebody who, yes, they had access to the box, so the next thing they did was they went and hacked your CI code to jump to whatever to make life, get their hack in?
I think, and maybe I'm misunderstanding, but I think what you're saying is somebody who's already on the wrong side of the security door has access to change this thing. And I think if they have access to change this thing, they have access to change the class files that are inputs, they have access to change the VM.
Suppose they're on but not root, but they're instead the build ID person. Yeah. Is there any reason to think that they should or should not, or something you should do about that? Like if they got root, yeah, you're right, nothing, it's all dead already.
But I think if they're in that position, they have the opportunity to change the class files that we're using as input. It's not the compiled code that, right? You can go write an agent and modify the class files so you already own us.
Yeah, okay, thank you.
It's no new exploits.
Hi there, thank you for the talk. With respect to the ergonomics of training runs, is there any eventual goal towards getting to like one application with one argument that trains when it needs it, adapts when it needs it, uses it when it needs it, can kind of, instead of having the multi-step kind of explicit process?
There is investigations into different options we can use to make it so you can say, hey, I'm going to run my application. If I have a cache, great, use it. If I don't, that must mean I'm a training run, generate one, and then I'll use it the next time. So we do have some investigation into changing the kinds of arguments that we can use to make that a little easier. The challenge is not everybody wants the same kind of behavior. Some people want that, give me one magic option and it does everything. Some people want, I'm doing deployments and I want to do a canary deployment and I want to build that over here and then use it over there. People want different things, and so we're kind of trying to figure out all the use cases to provide a useful set of options.
Is training like resource intensive on top of like the typical demands of the application, or not so much? Or
I wouldn't call it resource intensive, but there is a cost. And we're working on trying to minimize those costs, but they are there.
So generally speaking, training should be thought of as either build or canary, but not so much production sample in the real world, because maybe that's going to put extra stress on things.
What we'd love to be able to do is turn training on all the time, right? That would be the easiest thing for everybody, is to be able to just, everything's always training, and sometimes I generate the AOT configuration out of it, or I generate an AOT cache. And so that is an end goal, but we're not there yet.
All right, thank you very much.
How do we know the training is getting dirty? Let's say I do one, and after a while, the application has changed too much. Like, how can I realize that and then just redo it? Is there a way to know it gets bad?
If you make too many changes to your class path, like if you change the libraries and things, just like with CDS, if you change the classes involved, we may say, oh, these things don't match anymore, and we can't use it. So there is a way to be notified. You can say, we had the XX AOT mode. And just like with CDS, you can say, I want you to use it, and if you can't use it, to fail starting. And so you have the same kind of XX AOT mode equals on, and that says if you can't use the cache, don't start the VM.
Okay, cool.
Why do we need to run a training run? Like, can't we just AOT everything or as much as possible without actually doing this run?
Are you familiar with JAOTC? So that was a previous set of experiments that said, okay, let's take an entire module and we'll compile the whole thing ahead of time. What you find is that that's too much code, and the code that you compile doesn't match the behavior of the application. right? One of the great things about the JIT is it's able to say, this is the path you took, I'm gonna compile that path, and I'm gonna throw all the other code away. You don't need it. And with something where you have to compile everything, you don't have that option. You just don't have the observations to speculate from.
Thanks.
Maybe I missed, where do you train? On which, do you train on the development machine? Do you have to push it into the cloud if you deploy in the cloud and train there, or how does it work?
So right now, we have not focused on making the code that we generate portable. So if you're using, let me step back. If you're using JDK24, training on one machine and deploying on another is fine. The more we do ahead of time code generation, the more we have to be careful about moving, even within sub-architectures that maybe we've compiled in a particular set of instructions that aren't applicable on all machines. And so there will need to be some additional investigation on portability of the code. I'm actually at time, I think, so happy to take more questions. Let me pack my stuff up and we'll sort of step down and keep talking.